right, so welcome. Today we're going to talk about stoichiometry solutions. So by the end of this lesson, you should understand how dimensional analysis is used to solve stoichiometry problems. So first off, I've used this word a couple of times. What is stoichiometry? Okay, so stoichiometry is the relationship of amounts of the reactants or products involved in a chemical reaction. So what does that mean? Well, here's the kinds of things that we're going to be doing. So given an amount of one of the substances in a chemical reaction, we can actually use stoichiometry. We can use this process to calculate the amount of a different substance in that chemical reaction. This is a very powerful tool. It can be used, let's say I know how much of my reactant I'm starting with, and I know that it forms several different products. I could actually calculate how much of each individual product should theoretically be produced during this chemical reaction. This is an important thing to understand. It's very important when we're talking about production. There's a lot of manufacturing plants around the Victoria area. And so this is an important thing that people in the production industry have to think about when they're putting things together to make products. They have to think about how much they're starting with and how much of their product they're going to be able to make with that. So here's an example problem from something we'll be doing in the classroom. Let's say that I start off with 4.65 grams of iron 3 hydroxide, and it decomposes and produces iron 3 oxide and water. Question is, what mass of the iron 3 oxide is going to be produced from this reaction? So we're going to write a balanced chemical equation for the reaction first, because it's the balanced chemical equation that tells us the relationship between the reactants and products. So the relationship between these different substances is coming from the chemical equation. This is a decomposition reaction. So we're starting off with this one single reactant, the iron 3 hydroxide. And it is going to produce the two products that were given to us, iron 3 oxide and water. Now, I feel pretty proud of myself for writing this equation, except I can see very clearly that this is not balanced. So the relationship has to follow the law of conservation of matter. I have to have the same number of atoms on the reactant side and the product side for each element. Matter can't be created, matter can't be destroyed. And in order to have a real relationship that I can use to predict the amounts of things being made, I have to have the right relationship. So we have to balance this out. And I can see first off that I have one iron on the reactant side, but there are two irons on the product side. So I can't start with one and end with two. I'm gonna have to double the amount of my reactant. That way I have two irons on the reactant side, two irons on the product side. Now that didn't just double the iron, it doubled this entire substance. And so now I have two iron 3 hydroxides on the side. I had 3 oxygens here, but we just doubled that. So instead of having 3 oxygens here, I now have 3 times 2, I have 6 total oxygens. Well, I have 3 here, and I have 1 more here, so I only have 4 on the product side. Now, I'm not sure whether I need to increase the amount of iron oxide or increase the amount of water. So let me look at the other element that's in this equation. We also had 3 hydrogens that we just doubled. So there were 3 hydrogens, and then we put a coefficient of 2 multiplying this particle times 2. So now instead of having 3 hydrogens, I have 6. Now hydrogen is only present in this product here, and currently I only have 2 of them, but if I tripled it, that would give me the 6 hydrogens that I needed. That also increases the amount of oxygen on the product side and makes all of my elements equal to each other from the reactant side to the product side. So you have to write the correct equation, and you have to make sure that it's correctly balanced so that it follows the law of conservation of matter and describes a real reaction that could possibly take place. Okay, so then let's think about the next step in solving a problem like this. Once I have that equation written, I need to go back to my problem. And I need to identify the known quantity that I'm starting with and the wanted quantity. So the known is what's given to you in the problem. So the known is the number and unit that's given to you in the problem. The wanted is the question that they're asking. So the wanted is the thing, the substance, the amount that we need to calculate. So let's go ahead and think about what our known is for this particular problem and what our wanted amount is for this particular problem. So let me flip back to the question. If I reread it, it says that I have 4.65 grams of iron 3 hydroxide. This is an amount given to me in the problem. So this is the known quantity right here. The question is what mass of iron 3 oxide is produced. So we need to figure out a mass of iron 3 oxide. So my known, 4.65 grams of iron 3 hydroxide. And my wanted is I need to figure out how many grams, because that's the unit for mass that we use in chemistry. I need to figure out how many grams of iron 3 oxide are going to be produced. The next step is the thing that makes stoichiometry unique. We're going to determine the mole ratio. And this is really the relationship between these two different substances that we're dealing with in this problem. Okay, the mole ratio is the ratio of the coefficients of the known and wanted substances in the equation for the reaction that we're dealing with. So we really need to look at the coefficients of the known substance and the coefficients of the wanted substance in order to determine that mole ratio. So I'm going to go back to my balanced chemical equation. And before we come up with the mole ratio, I want to look at the equation in sort of a different way. I want to think about it like this. For every 2 iron hydroxides I start with, I'm going to end up producing 1 iron oxide and 3 waters. So that's another way to look at this reaction. I'm going to start off with 2 of these, and every time 2 of these react, I'm going to get 1 of these and 3 of these. Now, we weren't asked anything about the water. So it wasn't our known substance, it wasn't our wanted substance, and although it's an important part of this chemical reaction, it's not something we really need to worry about in the problem that we're trying to solve. What we need to do is find the relationship between the known substance, which was the iron hydroxide, and the wanted substance, which was the iron oxide. And what we know is that for every 2 of these that react, we're going to end up with 1 iron oxide. So that's our mole ratio right there. For every 2 moles of FeOH3 that react, we're going to end up with 1 mole of Fe2O3. That's our mole ratio. So the mole ratio is simply the ratio of the coefficients of the known and wanted substance in the chemical equation. Okay. So then let's talk about how we're going to plan our solution. And that mole ratio that we just determined is really the thing that connects the known substance to the wanted substance. I'm going to draw a little line here, and everything on this side of my map is going to be for the known quantity. And everything on this side of the map is going to refer to the wanted substance, the wanted quantity. So we could be given our amount of known in different ways. In this particular problem, they gave us a mass of our known material. So we knew we had a certain number of grams to start with. We could be given mass like that in other problems. We could be given our starting or our known amount in moles instead. Or we could be given a starting amount of particles. And by particles, it could be atoms, or it could be molecules, or it could even be formula units. The connection between our known substance and our wanted substance is a mole ratio, which means no matter what unit we're given, we have to convert it to moles. We've already done this before, and we know that if we're given a mass of something, and we want to convert it to moles, that it's the molar mass from the periodic table that's going to be our conversion factor between those two things. I can take my mass that I'm given and use the molar mass to convert it to moles. Now, if I'm given moles to start with, I don't have to do any conversion. I can go right to the mole ratio and use that to connect my known substance to my wanted substance. If I'm given particles, and again, my relationship between substances is a mole ratio, I've got to convert particles to moles. And so in order to do that, we would use Avogadro's number, 6.02 times 10 to the 23rd. That would be the conversion factor that we would use to convert particles to moles before we use the mole ratio to connect our known and wanted substances. Now, just like our known amount could be given in different units, we could be asked to find our wanted amount in different units. We could be asked to calculate a mass like we were in this problem. We could be asked to give the answer in units of moles, or we could be asked to give the answer in units of particles. And again, particles are either atoms, molecules, or formula units. And just like before, if I'm going to go from moles to mass, I know that it's the molar mass on the periodic table that's going to serve as my conversion factor. If I need my wanted substance in units of moles, I'm done after the mole ratio because that's exactly the unit it's in. If I need my answer in units of particles, then after I use the mole ratio to turn my known substance into my wanted substance, after I use the mole ratio to connect those two different substances, then I can turn my wanted quantity into particles, again using the conversion factor of Avogadro's number, 6.02 times 10 to the 23rd. So what we're going to do is use those conversion factors in the order that we determine using this mole map up here in order to set up our dimensional analysis. And for our particular problem that we're working, we were given grams of our known quantity. So we're starting off with a known amount in grams. We're going to use the molar mass first to convert it to moles. Then we're going to use the mole ratio to connect our two substances. And once I've determined how many moles of my wanted are going to be produced using the mole ratio, I'm going to use the molar mass of my wanted substance to turn it back into grams, because we were asked to find the answer in units of grams. So those are going to be the three conversion factors that we use, and that's going to be the order in which we use them. So I'm going to start off with my known amount. I'm going to use the molar mass of my known amount to convert it to moles. Then I'm going to use the mole ratio to turn moles of my known into moles of my wanted. And then I'm going to use the molar mass of my wanted substance to determine my final answer. As we're setting this up, we need to make sure that the units for all of our conversion factors cancel out, and that's really the key to dimensional analysis. Our units must cancel out from top to bottom in order for dimensional analysis to work. So again, when we're doing dimensional analysis, always, always, always start with the known amount from the problem. So again, in the problem, we were given 4.65 grams of FeOH3. Draw my lines. And just like always, we're going to drop the unit down here. So I know I'm starting with 4.5 grams of FeOH3. So information about grams of FeOH3 has to go down here in order for those two units to cancel out. We already said that our first conversion factor is going to be the molar mass from the periodic table. So that mass is going to go along with the unit grams down on the bottom. And that mass from the periodic table is always equal to 1 mole of that substance, FeOH3. Now, in order to fill that in, I need to look up those elements on the periodic table and add their masses together, keeping in mind that I really have 3 oxygens and 3 hydrogens in this chemical formula. So if I look up the mass of iron is 55.845. To that, I'm going to add, and in parentheses, I'm going to multiply 3 times the mass of oxygen, close my parentheses, plus, and then open parentheses, 3 times the mass of hydrogen. So I'm adding together iron's mass from the periodic table, 3 times the mass of oxygen, and 3 times the mass of hydrogen, because I have 3 of each in this chemical formula. So the total mass for this particular compound is 106.866. But we're not done yet. All I've done is simply convert my known amount in grams to moles. What we're going to do next is we're going to use the mole ratio to convert the known substance to the wanted substance. Now again, if I look at my mole ratio, what I know is that for every 2 moles of iron hydroxide I start with, we're going to produce 1 mole of iron oxide. So I'm going to use that as the conversion factor. For every 2 moles of iron hydroxide I start with, we're going to produce 1 mole of iron 3 oxide. And again, I need to make sure that my units cancel out from top to bottom. So what I know about moles of iron hydroxide was on the top. I carried that unit down to the bottom of this conversion factor so that it'll cancel out. And this should actually be a 3 right here. So again, moles of FeOH3 here, carry down that unit. And what I know is that for every 2 moles of iron hydroxide that react, we're going to produce 1 mole of iron oxide. But I wasn't asked for the answer in units of moles. I was asked for the answer in units of grams. So that's going to be the very last step here. We need to convert moles of our wanted substance to mass. And again, the conversion factor we use for that is the molar mass from the periodic table. In my dimensional analysis, I'm going to go ahead and carry that unit down. Mole Fe2O3. And what we know is that 1 mole of any substance is equal to its mass on the periodic table. And we have to keep in mind that there's 2 irons and 3 oxygens in this chemical formula. So I'm going to multiply 2 times the mass of iron, and then I'm going to add 3 times the mass of oxygen. And I get a total mass of 159.687 grams, equivalent to 1 mole of this substance. This dimensional analysis has units that cancel out from top to bottom, and all of my units cancel out except for grams of the iron 3 oxide. So this is going to be the unit on our answer. By setting this up, we've converted a starting amount of one substance to an amount of a different substance in the chemical equation. So the very last step in this process is to actually do the calculation. So the first thing we do is we multiply across the top of our dimensional analysis. Then we multiply across the bottom. We'll end up with 2 separate products. So we have a product for the top, and then separately multiply and find a product for the bottom. It's going to be that top product divided by the bottom product that gives us our final answer. And we're going to have to round that answer to contain the correct number of significant figures. So that'll be how we solve all of these dimensional analysis problems. I hope this helps you guys set up and solve stoichiometry problems.